Welcome to this presentation where I will discuss the computation of the motion of particles. In particle-based simulations, 3D objects are subdivided into small volumes, which are referred to as particles or elements. Now for these particles we perform two tasks. We compute forces and we apply the forces to update the velocities and the positions of the particles. The force computation varies and is mainly determined by the material of a particle. So obviously we compute different forces at fluid particles or at deformable particles. As the force computation is a larger topic and as the usefulness of the forces remains rather unclear when we don't know how to apply the forces, this course first starts with the discussion of how particle forces are used to update velocities and positions of particles. So we assume that we know the forces at a particle and that we can compute the forces. Now, this presentation focuses on the question how to compute positions and velocities of particles over time given the forces that act at the particles. Here we have the outline of the presentation. I start with a more general introduction to particle-based simulations in order to provide you with an intuition of what particles are, why there act forces at the particles, and how particles move. Then we start to focus on the motion of particles. I will introduce some notation, the governing equations for the particle motion, and I will give a simple example of particle forces. Here we will basically see all the relevant aspects of the problem that we have to solve when we compute particle trajectories over time. Then we briefly look into finite differences, which are one simple way to illustrate the idea behind the methods that we will investigate for the computation of the motion of particles. Now in the main part of the presentation we look into so-called numerical integration schemes. We will see that the motion of particles is governed by a system of two first-order differential equations, which can also be written as one second-order ordinary differential equation. These equations govern the desired unknown particle velocities and positions over time, and we will look into a variety of schemes to approximately reconstruct the unknown particle trajectories. I will not only discuss various numerical integration schemes, but I will also try to motivate why it is relevant to consider several options here. And when I discuss the integration schemes, I also focus on the application and I will discuss relevant implementation aspects. I will also discuss performance aspects and other relevant points. But first we start with the general introduction to particle-based simulations. We are generally interested in the dynamic simulation of various types of objects over time. In particular, we will look into the simulation of rigid bodies, deformable objects, and fluids. On the right-hand side we see three states of some simulated cloth that interacts with a rigid sphere. And for the 2D cloth, we see its particle representation. So the entire surface of the cloth model is sampled with particles. We compute forces at the particles due to deformations of the cloth and due to contact with the sphere and with the ground. And then we update the particle positions and velocities accordingly. Here we have the respective video sequence. Again, we see the particle representation of the cloth model, and you can see that the cloth model interacts with the sphere, and we also have self-collisions. And now all these contacts and also deformations of the cloth model and also gravity cause forces at the particles, which govern the movement of the entire cloth model. Here we have another example that particularly illustrates the versatility of particle-based simulations. We see particles of three different colors, and we also see that the particles can either be simulated as being part of a fluid or being part of an elastic solid. This basically shows that we can compute different forces at the particles. Here in this scenario, we either compute forces due to elastic deformations or we compute fluid forces. In both cases, however, we always compute contact forces between the particles and the surrounding container. Later in the course, we will see how to compute elastic forces and how to compute fluid contact forces. Now here in this presentation, we focus on the velocity and position updates that result from the forces. Whenever we simulate some model, we subdivide the model into small parts or particles. If we have a 3D volume, then we subdivide into small volumes. If we have a 2D model, then we subdivide into small surface patches. In 1D, we subdivide into line segments. Throughout the presentation, we typically ignore the dimensionality of a particle. we typically assume a volumetric 3D particle. Such particles represent some small part of an object, so they have a volume, and from the density rho of the material of the object, we can also deduce a mass m. Despite the fact that particles have a volume, we typically consider one representative position x of a particle and one representative velocity v of a particle. We also consider one force F at a particle. I also like to point out that particles can be of arbitrary shape. Sometimes we know the shape, sometimes not. Sometimes the shape is relevant, as for instance in elastic solids. Sometimes the shape is irrelevant, as for fluid particles. Now here on this slide we see an illustration of how particles can be used to represent a fluid. We start with a fluid body inside a container, and then we choose a user-defined number of particles to represent the fluid body. In this example, for instance, we have used 22 particles of the same size. Each particle has its representative position and velocity. We would compute fluid forces F, and each particle has some mass, volume, and density. The density rho is just the density of the fluid that we would like to represent. The volume V is given by dividing the overall volume of the entire fluid body by the number of particles, and the mass m can be computed from the volume and the density. You can see that the shape of a fluid particle is rather complex. On the other hand, the shape does not matter in the computation of fluid forces. Therefore, we generally do not estimate the shape of fluid particles in a simulation. And as we do not know the shape, we typically just render spheres to visualize the particles. But keep in mind that the fluid particles are not simple, perfect spheres. We are just too lazy to render the actual shape. Another example of a particle representation is shown here for a 2D cloth model. We see the original cloth model and its spatial discretization into small surface patches. Here, each surface patch is a triangle, and these triangles are typically referred to as elements. The colors in the image illustrate the amount of deformation or strain energy at the respective positions. Here in this case, the forces are computed for the elements. If a triangle deforms, or if two adjacent triangles bend with respect to each other, then we compute forces for such a deformed triangle. These forces are then applied to the particles which are centered at the vertices of the triangle. This is illustrated on the right-hand side. So originally we subdivide the 2D cloth model into triangles. Each triangle represents some mass and some area or volume according to the density rho of the cloth model. And if these triangles deform, we compute the respective forces. But then we apply the forces at the vertices, and we compute the motion of the vertices over time. Now the vertices can be interpreted as particles. They have positions, velocities, and forces, and one can associate a volume, a mass, and a density to such a vertex. For instance, if we have one triangle, we can say that each of the three vertices carries 1/3 of the overall volume and mass of the triangle. If we apply this idea to all adjacent triangles of the vertex in the middle of this illustration here, then we end up with a green region that illustrates the volume or area and the respective mass that is associated with the vertex. So again, in this case, we compute forces for the elements, which are the triangles, and we apply the respective forces to the particles, which are the areas centered at the vertices. The same concept holds for 3D particles. On the left-hand side, we see the triangulated surface of a 3D object that we would like to represent with particles. And on the right-hand side, we see a set of tetrahedra that approximately represents the volume of the object. Now, in a simulation, we would couple both representations. We would use the tetrahedra for the simulation and the triangulated surface mesh for the visualization. Here the tetrahedra are our elements for which we compute forces. If a tetrahedron deforms, if it is compressed or sheared, then we compute the respective elastic forces and we apply the forces to the particles that are centered at the vertices. Again, if we had just one element, just one tetrahedron, then we would get 4 particles, 1 particle for each vertex. We would divide the mass and the volume of the tetrahedron by 4 and associate the result to each vertex. Now the particles move due to the forces that act at the particles, and these forces result from various aspects. Typically we have a rest state where we consider the particles to be undeformed. Now we can compute forces when the particles get compressed, as shown in the illustration. Compression forces try to counteract the compression, and such forces can be observed in a variety of materials, for instance in fluids and in elastic solids. In other materials, however, for instance in snow, we do not necessarily have forces that counteract compression. Another example would be shear. If elements or particles are sheared, we compute forces to counteract the shear. Such forces occur, for instance, in elastic solids, but they do not occur in fluids. The next example is the force due to gravity. This force is typically applied to all particles for all materials. In addition to forces that result from particle displacements, we can also compute forces from velocities. For instance, if we have adjacent particles with different velocities, as indicated here by blue arrows, we can compute forces that counteract these velocity differences. An example for such forces are viscosity forces in fluids. And the last example force that I'd like to discuss are contact or constraint forces. Here, for instance, we have particles that should rest on the yellow contact plane. In order to realize such a scenario, we need to apply forces that cancel all other forces. The illustration, for instance, suggests that the contact forces point upwards in order to cancel the forces due to gravity that point downwards. Once again, this presentation assumes that we know how to compute the forces. As you can guess from the illustrations, the force computation is a larger topic, and we will address it after we know how to compute particle motions. Now here I'd like to discuss the equations that govern the motion of a particle. First of all, we have a governing equation for the particle position. We know that the time rate of change of the position is equal to the velocity. This is an ordinary differential equation, and it describes the unknown function x over time t in terms of its derivative. The second equation that we consider governs the velocity of a particle and is known as Newton's second law. The equation states that the force at a particle equals the time rate of change of its linear momentum. The linear momentum is given as mass m times velocity v, and if we apply the product rule, we get the sum of the time rate of change of the mass times the velocity plus the time rate of change of the velocity times the particle mass. Now, this is also an ordinary differential equation, and it governs the unknown function v over time in terms of its derivative. In summary, we have two governing equations for two unknown functions x and v that we would like to reconstruct. We typically assume that the particle mass is constant during a simulation, so the governing equation for the velocity typically simplifies, and we get these two ODEs that govern the particle motion. As I will discuss later, these two equations are a coupled system of first-order ODEs, which can also be written as one second-order ODE, as shown here. Now in this presentation I will discuss a variety of so-called numerical integration schemes to solve these equations. Some schemes focus on the representation with two equations, other schemes base on the representation as one second-order ODE. Now here we have a summary of the general concept of particle-based simulations. We start with an object that we would like to simulate. This object is discretized into small volumes or particles. Then we implement forces that act at the particles. These forces change the velocities of the particles, and the velocities change the particle positions over time. We also say that the particles are advected with their velocity. Now these steps are performed over and over again, and we end up with a particle simulation. That's it about the introduction to particle-based simulations in general. Now we start to focus on the question how to compute the trajectories of particles. I will introduce the employed notation, illustrate the problem that we would like to solve, and reiterate the governing equations that we use to solve the problem. So here we have a list of quantities that we typically consider at a particle to compute its motion. First of all, a particle represents some small volume of a material, so it has a mass m, which is just a scalar value. Then a particle has a position x and a velocity v. Position and velocity are represented with vectors, and we often work in 3D or 2D. So here we assume a 3D simulation. Then we also have a force F that acts at a particle. In addition to the force, we alternatively consider the acceleration a at a particle, which is force divided by mass. It depends on the context whether we work with force or with acceleration. In the context of the particle motion, it is often slightly more convenient to work with the acceleration, as we will see on the next slides. All the particle quantities are considered at certain discrete time points t. In a simulation, we always initialize the particle quantities at time t, and then we aim at computing the particle positions and velocities for future time points t plus some time difference h. So we discretize our object into particles, we define the respective particle positions x of t, and we also specify the velocities v of t. Considering the material of the particle and various other aspects, we can also always compute the particle acceleration a at time t. This acceleration is generally a function of some particle positions and velocities. So from positions x of t and velocities v of t, we can compute the acceleration a of t. Now we aim at computing the particle quantities at time t plus h using all the information from time t. In particular, we are interested in computing x of t plus h and v of t plus h. Using the position and the velocity at the next time point, we can also update the acceleration at the next time point, and then we can proceed with the computation of the particle quantities at time t plus 2h and so on. This provides us with our simulation result. So particle simulations are concerned with the computation of unknown future particle quantities from known current information. And various solutions to this task will be discussed in the presentation. Here we see the equations that govern the motion of a particle. We have Newton's second law that says that the acceleration at a particle is equal to the time rate of change of its velocity, and the second part of the equation encodes the fact that the velocity is the time rate of change of the position. So we have actually two ordinary differential equations, or ODEs. As already mentioned, these equations describe the functions x of t and v of t in terms of their derivatives with respect to t. And now we will see that numerical integration can be applied to these equations in order to approximately solve the functions x of t and v of t for future time points t. I would also like to reiterate that the governing equations can be written in two forms. First, they can be written as a so-called initial value problem of second order, where second order refers to the fact that the second derivative of the position occurs in the equation. So the second derivative of the position with respect to time is equal to the acceleration. In order to get a unique solution, we need to initialize the particle position x and the particle velocity v at some user-defined time point t0. That's why the formulation is referred to as initial value problem. The second form that can be used for the governing equations is to write it as a coupled system of first-order ODEs. In this form, we actually have two initial value problems of first order. We have one first-order ODE for the position, where the position x is initialized at time point t0, and we have another first-order ODE for the velocity, where the velocity v is initialized at time point t0. Here in this case, we have the same problem twice, once for the position and once for the velocity. Now this slide discusses our initial value first-order problems. We have two functions, x of t and v of t, that represent the particle motion. We initialize both functions at some user-defined time point t0. Now for each function, we have a governing equation. One governing equation for the position x that states that the time derivative of the position is equal to the particle velocity, and a second governing equation for the velocity that states that the time derivative of the velocity is equal to the particle acceleration. Now the question is how to estimate the position and the velocity at a nearby future time point t0 plus h. The problem is shown in this illustration. We have positions x over time t, and the dotted line indicates the actual function x over time t that we would like to reconstruct. The green point shows our known position x at t0. And the blue line at x t0 indicates the known velocity at time t0. The velocity is the derivative of the position, so the velocity can actually be interpreted as the slope of the function x of t at time t0. Now from the position and the velocity at time t0, we would like to compute the position x at time t0 plus h, indicated by the green outlined circle. How do we do that? One simple idea would be to assume that the function x is linear from t0 to t0 plus h. We could assume that the velocity is constant in between t0 and t0 plus h. And if h is just a small time difference, then this assumption is generally not too bad. For the velocity, we have exactly the same setting as for the position. The illustration shows velocity v over time t, and the dotted line is the unknown velocity function. We know the velocity at time t0, we know its derivative at time t0, namely the acceleration, and we would like to predict the velocity v at time t0 plus h, indicated by the green outlined circle. Again, one simple approximate solution would be to assume that the acceleration in between t0 and t0 plus h is constant. Then current velocity plus h times current acceleration would give an estimate of the velocity at the next time point. Despite the fact that we do not address force computations for different materials in this part of the course, I'd like to at least show one example force or acceleration so that you get an idea of how forces are typically computed at particles. Here in this example, we have two particles that are connected by an elastic spring. So we have two particle positions x1 and x2 and two particle velocities v1 and v2. And I'd like to illustrate how the acceleration at particle 1 can be computed. The important point here is to note that the acceleration of a particle does not only depend on its own position and velocity, but it also generally depends on the positions and velocities of other, typically nearby particles. So here for the spring, the force at particle 1 depends on quantities from particle 1 and 2. Later, when we talk about accelerations at fluid particles, we will see that the acceleration at a particle can even depend on 30 or more positions and velocities of adjacent particles. So here for the spring, the actual computation of the acceleration is not too involved. We compute the difference between the actual spring length and the desired rest spring length, which represents the deformation of a spring. This deformation is multiplied with some user-defined stiffness constant k, which gives the magnitude of the spring force. This force magnitude is multiplied with some normalized direction between x1 and x2 to get the actual force. And finally, the force is divided by the mass m1 of particle 1 to get the acceleration a1 at particle 1. When using springs in simulations, we often use some sort of damping. For instance, one can damp the relative movement of the two particles. Therefore, we could consider the magnitude of the velocity difference between particle 1 and 2 projected onto the spring direction. If we multiply this with the normalized spring direction, we get a force in spring direction, which can be multiplied with a user-defined parameter gamma. Finally, the term is divided by mass m1 to get an acceleration. Once again, the details are not too important here. However, it's important to keep in mind that particle accelerations or forces generally depend on the positions or velocities of other particles in a simulated object. I would also like to point out that the computations of particle accelerations are generally expensive. If you have a particle that is connected to, let's say, 100 other particles with springs, then you have to compute 100 spring forces to get the particle force. Or it might be required to execute additional algorithms to compute a force. For instance, collision tests might be required to find out whether there are some contacts for which we have to compute contact forces. So the force or acceleration computation at particles is typically expensive. That's it about the introduction to particle motion. I've introduced some notation, I've illustrated the problem and how to use the governing equations, and finally I've introduced one example force that can act at a particle. Now in the following, I'd like to briefly discuss one option to illustrate the idea behind numerical integration based on finite differences. Here we consider our function of positions x over time t and start with a Taylor series that approximates the position at the next time point. So x of t plus h can be approximated with x of t plus the time derivative of x at time t, and O of h squared indicates the order of the truncation error that we get with this approximation. We now divide the equation by h and solve for the derivative. What we get is a finite difference approximation of the derivative of x. So the derivative of x at time t on the left-hand side can be approximated with the difference of the positions x at t plus h and x at t divided by h. Again, we see the order of the respective errors that we get with this approximation. Now we can use such an approximation to replace continuous derivatives in our governing ODEs with discrete finite differences in order to get a so-called FDE, or finite difference equation. This is illustrated here for both governing equations that we use for the particle motion. We start with the two ODEs that state that the time derivative of the position is equal to the velocity and that the time derivative of the velocity is equal to the acceleration. Now we use the finite difference approximation in order to replace the continuous derivatives, and we get two FDEs. When we look at these two equations, we see that they contain quantities at time t and at time t plus h. We know x of t, v of t, and a of t, while x of t plus h and v of t plus h are unknown. And we remember that it is actually our goal to compute the particle position and its velocity at time t plus h based on known particle quantities at time t. Now this goal can be achieved by solving both equations for the respective unknown at time t plus h. And these two equations are a first option to solve our problem. We see how to approximately compute the position x at t plus h with xt plus h times vt, and we can compute the velocity v at t plus h as vt plus h times at. These two equations actually solve our problem and can be used to reconstruct the particle positions and velocities over time. Each of these two equations is referred to as explicit Euler update. So we see an explicit Euler update for the position and another one for the velocity. Here on this slide, we see another option to illustrate how to approximate a continuous derivative with a finite difference that can be used to get an FDE from an ODE. Here we assume that our function x of t is linear near time point t. This means that we can represent the function x of t as a line with b times t plus c, where b is the slope of the line and c is an offset. The slope of the line is given by the derivative of x at time point t, and the offset can be computed accordingly. Now we use the assumption that xt is a line in between t and t plus h. This means that x of t plus h can be computed as the derivative of x at t times t plus h plus xt minus the derivative of x times t. This equation can be solved for the derivative of x at time t, and we get the same finite difference approximation for the derivative that we have already seen on the previous slide. That's it about the introduction to particle motion, to the problem that we solve, and to the governing equations. We have also seen a first simple solution to reconstruct particle trajectories. Now in the following I will discuss a variety of alternative schemes that can be used to compute the particle motion. I will explain the methods and also discuss implementation aspects. I will also discuss pros and cons, and will also try to motivate why we consider various integration schemes. The integration schemes can be classified in various ways. Here I mainly distinguish explicit and implicit schemes, and I also briefly introduce so-called predictor-corrector schemes. The first scheme is the explicit Euler update that I've already briefly mentioned a few slides ago. We start with our governing equations, which are a system of first-order ODEs, and we assume that we know our particle quantities at some time point t0. So we know the particle position, its velocity, and we can compute its acceleration. We also define some time difference or time step h. Now the explicit Euler update is used twice, once for the position update and once for the velocity update. We see that the Euler scheme allows us to compute an unknown position at t0 plus h from known particle quantities at time t0. And the velocity is updated exactly the same way. We can also see the order of the truncation error. So here the truncation error is of order 2. It might be slightly confusing, but the Euler scheme is always referred to as a scheme with first-order accuracy. This classification refers to the fact that the Euler scheme bases on an approximation of the time derivative that is of first-order accuracy. So the truncation error is second order, but the error of the Euler scheme is first order. On slide 22, you can actually see both error orders related to the Euler scheme. When computing the trajectories of particles, we update positions and velocities. Here it's important to keep in mind that both updates are coupled. The position update depends on the velocity, and the velocity update depends on the position. That's why it's typically not possible to just update one quantity independent from the other one. This is also the reason why we say that the governing equations are coupled, or we say that we have a coupled system of ODEs. The coupling is illustrated here for two simulation steps. In the first update from t0 to t0 plus h, we see that we need the velocity to update the position, and we see that we need the acceleration to update the velocity. Now here we remember the spring force example, where I've discussed that particle accelerations generally depend on positions and velocities. And that's why the velocity update actually depends on particle positions and velocities. In the second simulation step from t0 plus h to t0 plus 2h, we use the velocity at t0 plus h in the position update, and we use the position and the velocity at t0 plus h to compute the acceleration that is required for the velocity update. In addition to the explicit Euler scheme, there exists a large variety of alternative numerical integration schemes. Now, before we look into selected variants, I'd like to motivate various properties that the schemes might have, and I'd like to discuss why it can be relevant to investigate different schemes dependent on the scenario. First of all, we remember that we use an approximation where we replace a continuous ODE with a discretized FDE. That's why we end up with a discretization error when we solve the FDE instead of the original ODE. Now we say that an FDE representation of an ODE is consistent if the discretization error converges to 0 if the time step approaches 0. So in a consistent scheme, the error should get smaller if we use smaller time steps. We further say that the scheme is stable if previously introduced errors are not amplified within a simulation step. So in each step, we introduce an error. This error can be smaller or larger, but this is not a problem. Only if previously introduced errors are amplified, then the scheme is unstable. In practice, unstable schemes can be recognized by diverging positions and arbitrarily growing velocities, which we also call explosions. If a simulated object explodes, the employed scheme is unstable. Now, the third property is convergence. We say that a scheme or an FDE is convergent if the solution of the FDE approaches the solution of the ODE. This basically means that both the FDE and the ODE should provide us with solutions of the same problem. Now, all the integration schemes that we will consider in this presentation are actually consistent. So if the time step gets smaller, the discretization error is reduced. On the other hand, each simulation step always introduces some error. And if the previously introduced errors are not amplified, then a finite difference scheme is stable. Finally, if a scheme is consistent and stable, then it is convergent. In other words, if we use a consistent scheme, and if our simulation does not explode, then we solve the correct problem. And if the time steps get smaller and smaller, and if the used elements or particles get smaller and smaller, then our simulation result converges to the correct solution. As all of these schemes that we use are consistent, we just have to check whether our simulation explodes. If not, we are doing the right thing. So stability is an important property in our simulations. In practice, however, it turns out that it's rather involved to theoretically analyze the stability of a complex simulation, and it can also be involved to guarantee a stable simulation behavior. We distinguish two cases. First, a scheme is called conditionally stable if the stability depends on some parameters, for instance, the size of the time step. If a scheme works for small time steps but not for large ones, then it is conditionally stable. Second, a scheme is called unconditionally stable if it's stable under all circumstances, if it particularly works for all time steps. If a scheme never works, it would be unconditionally unstable. Now, very often we see conditional stability, where the stability depends on some parameters of a simulation. For instance, the ODE, the FDE, the time step, and also the particle quantities can influence the stability of a simulation. Here I'd like to particularly point out that a numerical scheme by itself is not stable or unstable. For instance, the explicit Euler update is not generally good or bad. Its stability actually depends on the scenario. If explicit Euler is used to simulate a spring without damping, we are unconditionally unstable. This combination never works, no matter which time step or which particle properties we choose. A spring with damping, however, can be conveniently simulated with explicit Euler. Now, generally, we are interested in schemes that potentially provide our simulations with improved stability. This is due to the fact that an improved stability allows us to work with larger time steps, which reduces the overall number of simulation steps that have to be computed, which in turn reduces the overall computation time. So in terms of performance, we are typically interested in large time steps, and that's why we consider different numerical integration schemes. This is also discussed here on this slide. If we can choose larger time steps, then we need to compute less steps, and the overall computation time is probably reduced. The illustration here indicates the simulation steps that we compute for two different time steps h. If h is smaller, then we need more time steps to compute a certain time frame. If h is larger, then we compute less steps for the same time frame. And now different finite difference schemes typically allow for different time steps. For instance, schemes have different error orders, and for explicit schemes, a larger error order corresponds to an improved stability, and we can work with larger time steps. On the other hand, more accurate schemes might also be more expensive to compute. That's why we are interested in stable schemes with a maximized ratio between time step and computing complexity per simulation step. Once again, schemes that allow for larger time steps can be more expensive. And as we try to optimize the performance of our simulations, we look at the ratio between the time step size that can be chosen and the computing complexity per step. Now here on this slide we see a first alternative to the explicit Euler scheme, namely the midpoint method, which belongs to the class of second-order Runge-Kutta schemes. In order to get familiar with the illustration, we first look at the illustration of the Euler scheme. We have positions or velocities over time. So the green dot at time t can either indicate a position or a velocity. Accordingly, the red arrow at t is either the derivative of a position or a velocity. The dotted line is our function that we would like to reconstruct, and the green outlined circle at t plus h would be the correct solution. Again, either a position or a velocity. Now, if we apply the Euler concept, then we assume that the function is linear in between t and t plus h, and we compute the green filled circle at t plus h instead. So in such an Euler update, we use one derivative, which particularly means that we have to compute one particle acceleration for the velocity update. This fact is important as it indicates the computing complexity of the scheme. The computation of the particle accelerations is generally the dominating task, and here we have to compute the accelerations once. In terms of the error, we have already seen that the discretization error is of order 2 and the scheme has error order 1. Now on the right-hand side, we see the midpoint method illustrated in the same way. The functions that we see here are either positions or velocities over time, and the red arrows indicate derivatives, either velocities or accelerations. Now in the midpoint scheme, we start with a known function value at t and with a known derivative marked with 1. Now we make an Euler update, but we use only half of the time step h. This means that we get an estimate of our function at time t plus 0.5 h. Now for this intermediate value, we compute another derivative, here marked with 2. And finally, we take this derivative, apply it to the original function value at t, and make an Euler update from t to t plus h. In contrast to Euler, this update requires two derivatives. So roughly the computation is twice as expensive as the computation of an Euler step. It also requires intermediate positions and velocities, which is not the case for Euler. But on the other hand, the error order is larger, which means that the error is typically smaller and we can typically use larger time steps. Now here we see how to implement the midpoint method for an elastic spring. We start with two particles x1 and x2 with velocities v1 and v2 at time t. From these quantities we can compute the accelerations a1 and a2 at the particles. As a first step, the midpoint method performs an Euler update with half of the time step h. So we compute intermediate positions x1 star, x2 star, and also intermediate velocities v1 star and v2 star. From these intermediate quantities we can compute the intermediate accelerations a1 star and a2 star, which use the intermediate positions x star and velocities v star. And then finally we use the intermediate velocities v star to update the positions from t to t plus h with an Euler step, and we use the intermediate accelerations a star to update the velocities from t to t plus h. All these computations are shown here just for particle 1, but they are exactly the same for particle 2. The important point to note here is that we need to compute and store all intermediate positions and velocities before we can perform the last step in the midpoint scheme. It would not be correct to process particle after particle. If we just compute the intermediate position and velocity of one individual particle, we are not able to accurately compute the intermediate acceleration at that particle. In order to do so, we generally need all intermediate positions and velocities. Due to the significance of this implementation aspect, I've visualized the implementation here for one particle. We start with the current state at time t with known position and velocity. Now we need the derivatives. The velocity as the derivative of the position is given, and the acceleration as the derivative of the velocity can be computed from all positions and velocities. Next, we perform the first Euler update of the midpoint scheme to get the intermediate or predicted positions and velocities x star and v star for all particles. Based on this information, we can compute the intermediate or predicted accelerations a star at all particles. And finally, we use v star and a star to perform the second Euler step to get the final positions and velocities at time t plus h. The midpoint method is actually one variant of a second-order Runge-Kutta scheme. Now here on this slide we see a second option, namely the Hoyne scheme. The Hoyne scheme has the same error as the midpoint method, and it also requires two derivatives, but computes and uses the derivatives in a slightly different way compared to the midpoint method. Now the concept is shown here in this illustration. As always, we start with a function value at time t, and we know the derivative of this function at t marked with 1. Now we perform an Euler step from t to t plus h and take the result, either x star or v star, as an intermediate value. We also compute the acceleration a star from x star and v star. Now we have two derivatives for each function, one at time t and one at time t plus h. For the position, for instance, we have its derivative vt at time t and its derivative v star at time t plus h. The same holds for the velocity. Now in the final update step, these two derivatives for each function are averaged, and the result is used to get from t to t plus h. So similar to midpoint, we perform two Euler updates, but here we use the same time step h in each update. And again, the general properties are the same as for midpoint. We compute two derivatives and, as the name suggests, the error order is 2. The third variant shares the same basic properties of all second-order Runge-Kutta schemes, but slightly differs in the computations. We start with our function values x and v at time t, and we compute the derivative a at t. Then we perform an Euler step using 2/3 of the time step to get intermediate values x star and v star, which allow us to compute a star. And finally, we take a mixture of both derivatives for each function to perform a second Euler update from t to t plus h to get the final values. So midpoint, Heun, and Ralston are three variants of second-order Runge-Kutta schemes. Second order refers to the fact that the schemes are of second order, and in all variants we need to compute derivatives, in particular accelerations, 2 times. In addition to second-order Runge-Kutta schemes, there also exist fourth-order Runge-Kutta schemes, and here on this slide we have one variant. At a first glance, the illustration might look confusing, but the scheme is conceptually pretty much the same as the schemes on the previous slides. Here we just use more intermediate values, we compute more derivatives, and we perform more Euler updates. Once again, we start with position and velocity at time t. Here we compute the first derivative, namely the acceleration at time t, using xt and vt. Now we perform a first Euler update with 1/2 of the time step and get predicted or intermediate values x star and v star. With these values we compute a second derivative, namely a star. Now we perform a second Euler update. Again, we start at t and get from t to the middle of the time step, but here we now use the predicted derivatives v star and a star. The resulting values are x star star and v star star, a second set of intermediate values. For these values star star, we compute our third derivative a star star. This leads to the next Euler update, this time from t to t plus h, and here we use v star star and a star star as the respective derivatives. As a result of this Euler update, we get another set of intermediate values, x star 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 and v star star star. Again, we compute the respective acceleration a star star star. Now we are prepared for the final Euler update. In this final Euler update, we use a combination of the 4 computed derivatives to get from t to t plus h, and the resulting values are the final result of this Runge-Kutta scheme. As you can see, we need to compute 4 derivatives, in particular 4 accelerations. This means that fourth-order Runge-Kutta schemes are 4 times as expensive to compute compared to an Euler update. On the other hand, the error order is larger, which indicates that we can work with larger time steps. In terms of the implementation, this scheme is very similar to the previous schemes. But instead of computing one set of intermediate positions and velocities, we have to compute and store 4 sets of intermediate or predicted positions and velocities. And please keep in mind that each set star or star star or star 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 has to be computed simultaneously for all particles. It would not be correct to perform the steps on this slide for all particles one after the other. Here on this slide we see a second, less famous variant of the fourth-order Runge-Kutta scheme. I do not go through each of these steps, as they are very similar to the steps on the previous slide. We compute 4 accelerations and we perform 4 Euler updates. Now here I'd like to show and discuss a graph that illustrates the application of different explicit integration schemes to some known function. The purpose here is to illustrate the error that we introduce with each of these schemes. It is difficult to see, but there is a smooth red line which is the given correct solution. All other curves indicate a result that we get when we apply Euler, second order or fourth order Runge-Kutta. In these cases we evaluate the given function and its derivative at selected values as indicated by the markers, and we move from marker to marker with the time step h or h divided by 2. As you can see, the Runge-Kutta schemes are closer to the exact solution, while the Euler scheme is less accurate. We also see that the accuracy of Euler is improved when we use smaller time steps. For the blue curve, a time step of h divided by 2 has been used, while for the purple curve, the time step was h. It is also interesting to note once again that we have the error order on one hand and the actual error on the other hand. Let's imagine the given function would just be a line. In this case, all schemes would always compute the exact result without any error for arbitrary time steps. Of course, this is an artificial example, but it nevertheless shows that the error order is just an indicator of the accuracy of a scheme, but the actual accuracy also depends on the scenario that we simulate. In our simulations, we are of course interested in stability, but if a simulation is stable, then we want to optimize the performance. In terms of the explicit schemes that I've discussed, we have seen that we compute different numbers of derivatives, and I've discussed that the overall computation time of an integration scheme is dominated by the computations of particle accelerations. As we compute 4 accelerations in Runge-Kutta 4 compared to 1 acceleration in Euler, the Runge-Kutta scheme is 4 times as expensive as Euler. For Runge-Kutta 2, we have a factor of 2 accelerations in Runge-Kutta versus 1 acceleration in Euler. On the other hand, we have seen that additional derivatives improve the error order. So Runge-Kutta 4 is more accurate than Runge-Kutta 2, which is often more accurate than Euler. And here we see the respective error orders of the discretization error. These differences in the error order have the potential for different maximal time steps that can be used with these schemes. So potentially the largest time step can be used in Runge-Kutta 4, while Euler requires the smallest time step. Now we have seen that we are interested in maximizing the ratio between time step and computation time. This idea is illustrated here in an example where Runge-Kutta 4 runs with a time step that is 4 times larger than the time step for Euler. In this case, the overall computation time is the same for both simulations. And here we see the reason. Runge-Kutta computes 4 derivatives and is 4 times as expensive as Euler per simulation step. On the other hand, Euler requires 4 times more simulation steps as Runge-Kutta because the time step in Runge-Kutta is 4 times larger. Now finally, these two aspects cancel and the overall computation time is the same. This means if Runge-Kutta 4 runs with a time step that is larger than 4 times the time step of Euler, then Runge-Kutta is more efficient, otherwise Euler is more efficient. And again, this comparison is only practically relevant if the simulations are stable in all the discussed cases. And here on this slide, I'd like to reiterate that the particle accelerations dominate the computation time for a simulation step. It significantly matters whether the accelerations are computed once, 2 times, or 4 times. The computation of a spring force might be efficient, but other forces, for instance contact forces, can be very expensive when additional problems have to be solved to compute such forces. That's it about the first presentation that addresses particle motion. Thanks for your attention.